Hi everyone, we're going to start with carboxylic acids again, part 2. This question here is about why carboxylic acid is less reactive at the carbonyl carbon. So normally we think of that as being partially positive and a nucleophile would attack there. But why is it that carboxylic acid is not so reactive here? Well, I think if you recall that when you have a nucleophile, there's a competition between attacking at the carbonyl and attacking this hydrogen, because this is also partial positive. So you have multiple partial positive sites. And in fact, this one is usually favored because you get the resonance stabilized conjugate base like that. So that's why with very strong bases and good nucleophiles, you might get attack here instead. So the problem with that then is, how do we change carboxylic acids into other things if we can only grab this hydrogen? So one way to get around that is to convert the carboxylic acid to something else. And why not convert it to the most reactive compound on our ladder of derivatives? So it goes carboxylic acid and amides, and then esters, and then acid anhydrides, and then the most reactive acid halides. So this is actually a reaction you learned before. Hopefully last quarter you remember changing alcohol groups into halogens. And we used either SOCl2 called thionyl chloride, or SOCl. We can change that to a chlorine, or we can use PBr3 as a source of bromine and change it to an acid bromide. Okay, so it's a pretty similar reaction, but now we have this carbonyl group that gets involved in the mechanism. So here's the mechanism for this. I'm sure we can work it out together. We have thionyl chloride, or SOCl. This looks like an acid halide, doesn't it? It looks like this over here. This sulfur is partially positive and very much wants a nucleophile to come in and sort of displace this chloride, just like we've seen with the other nucleophilic addition-elimination reactions. So then you might ask, well, how can this be a nucleophile then for this electrophile? So how can this molecule attack here? So one thing you might want to think about are the resonance structures of this. If I were to ask you, which oxygen do you think is more basic, this one or this one? Do you know the answer to that? Well, actually, it turns out that it's this oxygen up here, and that's because of the resonance structure I was showing you up here, where these electrons are actually delocalized, and you can have a negative charge up here. So I'll show you that right now. We can, by resonance, point those upward, and then that will give us a negatively charged oxygen that we can use to attack. Okay, so right here in our next step, we'll do this. Okay, so I'm going to draw out this intermediate, and I'm not going to show all the arrows happening at once. I'm just going to show the nucleophilic attack, and then I'm going to show the elimination like this separately. And I like for you to do that too when you're asked for the mechanism. It's okay if you do it all in your head when you're just trying to figure out what you're going to make, and you just have to come up with the product. But when you're asked for a mechanism, it's nice to show all the steps. Now, in this, I'm also going to bring in a base. I could do that in the next step, but just to save time, sometimes a non-nucleophilic base like pyridine can be used just to soak up all the hydrogen ions. And now the chloride coming off here, sometimes I think the book shows chloride is grabbing this Cl, but I don't like to generate a strong acid. I don't think that's what's really happening. So they may only be doing that for the purposes of balancing this out. All right, once we have this then, you might notice that I have a chloride ion ready to add on to my carbonyl group here. And that's because I need a source of chloride, right? So this is our nucleophile for the next step. And chloride's not particularly strong base, but it is a good nucleophile because of its polarizability or its size. And it also helps that this is a good leaving group as well. And this is a good leaving group because of resonance, as well as its ability to decompose into sulfur dioxide and chloride ion, which are very stable. So this is thermodynamically driven. We're going to have this come in, go up, and again, we have another sort of tetrahedral intermediate again. And I like to show all the bonds because this next part is going to decompose. All right, so once we have this, you guys know what to do. We're going to, don't forget my chloride. We're going to generate the acid chloride right here, but I have to break a bond, so I'm going to break it off right here. Now, here's where it gets a little tricky. Like I said, this can decompose into something more stable than just this leaving group. So I'm going to show that here. I'm going to show that by making a double bond between this O and S. With this bond, I make another pi bond here. And then I can just have this leave like that. Now, technically, you could show this going up and this going down and this leaving, but just to simplify it, I'm okay with this. Okay, so here are all your intermediates right there and right there. So we've got 1, 2, 3, 4 steps to get to here. All right, so it seems complicated, but really it's just like with the alcohol going to the chloride. In the past, we had the alcohol attack the socle, but this time we have this little resonance structure and then attack by resonance this oxygen. It gets the negative charge, and that makes that oxygen more basic. Suppose the second step after acid chloride formation was ethanol and pyridine. What is the final product? So I mentioned sometimes we use a non-nucleophilic base. It's a bulky base, so it's not likely to attack anything nucleophilically. This is pyridine. So PYR sometimes is how it's abbreviated. So this lone pair can grab hydrogen ions. So second step after acid chloride formation, so we get the acid chloride. And then up here there's a little note that says it can react further. So if I have this, then I can react it again. So here's where it's really useful then to have this acid chloride, because the carboxylic acid would not react necessarily with these reagents, but an acid chloride's more reactive, so it will. So the idea is we're converting this to something more reactive, and then we can do whatever else we want to it, okay? So we're going to take this and use our ethanol and pyridine and try to figure out what's going on with that. Okay, so ethanol is our nucleophile. I can tell because this is my electrophile here. Okay, so now I'm just with the regular reactions where you attack and you release. Okay, so I'm going to have this. All right, and once I have this, just to get something different, I can release that. And I can also have pyridine. Before I do that, maybe I could have pyridine come in and take that hydrogen and make that less of a good leaving group. So maybe something like that. Or you can show them at the same time if you like. Okay, and then at this point, bring it down and release that. Okay, and hopefully you saw that we were going to make an ester, because here is our OR group. Okay, and we're swapping it out for that group, nucleophilic substitution. All right, so we end up with an ester. Okay, acid chloride to an ester. So here's another way then to do this. I think we learned before, if you have a carboxylic acid, you can just heat it with alcohol, ethanol, in a catalytic amount of acid, right? So the reaction we learned before was carboxylic acid and ethanol in H+. Will give us an ester. This is called acid catalyzed esterification. Okay, but remember with this that it's a reversible reaction. So it goes both ways. We have to mess with it with Le Chatelier by adding excess ethanol to make it the ester that's favored. But if we don't want to do that and we want it to be more irreversible, simply do this. This is way more reactive, so it's very much more product favored. And so you could take the carboxylic acid and Step 1, convert it to the acid chloride with SOCl2. So you'd say step 1, this, and then step 2, ethanol. Okay, and if you can remember to add pyridine, but otherwise it's sort of assumed. Okay? All right, so that's an alternative way to doing this esterification. Okay, so in this reaction, design a synthesis of how to make an amide from a carboxylic acid. And let's see if we can use the concept from before, because the issue with this is if you just try to use ammonia and you just want to switch that group out for ammonia, the problem with that, do you remember, is you'll grab this hydrogen and then you'll have this stable carboxylate and it won't want to react. So we've got to use the concept that we just learned and make this into something more reactive, make this into something more reactive, and then you can toss anything at it and make that, okay? Well, not anything, but you know what I mean. All right, so go ahead and try to figure out how to use what we just learned here to go from here to here. All right, guys, so hopefully you saw that we need to convert this to an acid chloride first because that's more reactive, or acid bromide. Sorry, I didn't say chloride has to be it. It could be a bromide here instead, but you have to use PBr3 instead. Okay, so that's fine. I will say chloride is used more commonly though. And then the second step will be to use ammonia. Since I don't have any R groups, and I just have a hydrogen that gets removed later, so I'll use ammonia for that. Okay, so that's how we synthesize from a carboxylic acid an amide. Okay, an amide from a carboxylic acid. All right, so here's some more practice with that. And notice when you start with a carboxylic acid, you might want to convert it to something more reactive first. And these are the problems that I think we skipped last time. So these will all use or can use the Sokal idea as your first step for carboxylic acid. Okay, so we did it. We went around that by using this reaction, I think, or something like that. Or no, we used LAH to reduce it to an aldehyde before. Let's see if you can use Sokal instead. And you will probably use that for these reactions as well. So go ahead and give that a try.